going through the usual headlines, there's this 3-week assignment, Project 3, which is due a week from tomorrow, not tomorrow, but a week from tomorrow. You can use our Project 2 solution as the basis if you want to. I will again remind people, it's really not a good idea to try to use RBFM for this assignment. Remember that the non-leaf nodes correspond to this, interleaving of page references together with keys. It really doesn't look anything like what we had in RBFM. And the thing that people really try to do is to make leaf pages of the index be things where you can use RBFM. But the leaf pages of the indexes don't have slots, and the values have to be kept in order so that you can do range searches. And it really is not the same as RBFM. And it's not all that hard to try to go ahead and to code the leaf pages yourself. Doing it via RBFM is not a good approach. If things happen to your teams, let me know and deal with that. You know about the midterm. You also at this point know about the grades on Project 2. We were relatively generous with respect to the grades on Project 2, which I hope people are happy about. We hope to be less generous on Project 3 and Project 4. There really are things where you should talk to Matthew and Saloni and try to get rid of all your seg faults. We do a lot of grading based on the code, not just on whether or not the tests work. And we'll continue to do that, but we really think that you should be getting rid of your seg faults before you hand in the assignments, not afterwards. So it'd be great to fix that. And again, I'll remind everybody, I have the midterms if anybody wants to pick them up after class, and I'm not using the microphone because I tried and the microphone didn't work. So if anybody wants me to speak louder, please go ahead and let me know. So now we're going to be talking about transactions. Again, it's going to be 3 lectures, about 6 classes worth of talking about transactions. And it'd be really easy to write a database system if you ran transactions serially. You run one transaction and then another transaction, and everything gets maintained consistently, except for the economics of your business. If you have a system that operates that way, your response time stinks, your throughput stinks, your scalability stinks. It's not going to end up working out. So, it's important to keep not just the disks, but also everything humming. You want lots of parallel stuff going on where you don't have to go ahead and wait for something to finish before you start something else. So there are a lot of different things that are going on inside an application program, but the database is, what's called the solipsist, good word, solipsism. Basically means it only cares about itself. It doesn't know about all the operations that are going on in your application other than the things that involve the database. And from the point of view, a transaction is all the stuff that's going on, which could involve stored procedures and functions, as well as updates and deletes and selects from the database and inserts. But the transaction is the database's view of the user program, which again, it views as a sequence of reads and writes. If there are things in the stored procedure where there are variables that are set, that's just control for executing things. The database sees the reads and the writes that are going on. So in effect, what's going on is, from the database's point of view, a bunch of reads and a bunch of writes. And the interaction of the reads and writes of a whole bunch of different transactions is going to be what we talk about when we talk about the properties of transactions. So again, you get concurrency by interleaving the actions of different transactions. You don't wait for one to finish before you start another. And the whole point is that you would like, now I'm about to tell you a small lie. As part of CODAs later, I will explain more about why it's a lie. But you really care about keeping the database consistent. You care about having the books balanced. You care about making sure you don't have constraints that are violated, that profit is equal to revenue minus costs, and all sorts of other things going on. And there are all these sorts of integrity constraints that we've talked about, and rules and so on inside databases. Constraints on domains, referential integrity constraints. The database knows what you've told the database to enforce, and the database tries to enforce and does enforce the constraints that you've told it about. There are other constraints that you may care about that the applications try to enforce themselves too. Okay? And the database doesn't understand the semantics of the data. It's stupid. It understands what you tell it to do. It understands the constraints that you tell it to enforce. And anything else has to be enforced by the way you're running the applications. Because the database doesn't understand that. And the issues are, what happens when you have the interleaving transactions and they interfere with each other? Or what happens when you're executing transactions and things go wrong? This gets kind of exciting. So we'll start off with a bank balance of 100. And I'm gonna run a transaction. We've seen this in 180. I see $100 and I want to be able to withdraw money. Is there enough for me to withdraw $25? Yeah, you know, withdraw the $25. My new balance is 75, the bank balance is now 75, that's the transaction, everything's cool. At around the same time, my wife, right, so from the database point of view, you read the account value, see whether it's greater than 25, pay the $25, subtract the $25, you know, write the new value of A, and that's gonna be a transaction. And we'll talk about the asset properties associated with transactions. But at the same time, what we potentially end up having happen is that there's a failure at the place where that line has been drawn. So what happens if you pay the $25 and the $25 haven't been taken out of the account? That would make the bank unhappy. What would happen if the balance was reduced to $75 and the $25 wasn't subtracted, well, what wasn't paid to me? That would make me unhappy. So you'd like to make sure that I get paid the $25 if and only if the balance got changed to 75. And there are interesting issues in doing that in case the crash happens there. But it could also be the case that my wife and I are both taking $25 out of the account. So we both, at around the same time, see that the balance is 100. And is there enough money to be able to pay $25? Yeah. So she sets the value to be 75 and gets paid 25. So do I. And the new bank balance is 75, and we both have gotten $25, which might make us happy, but might make the bank unhappy, because that $25 has been paid out twice, and the bank balance shows up as if it's 75, when it should actually be 50. So crashes are a problem, and interleaving of transactions ends up being a problem. Writing that $75 twice doesn't have the effect that you want to be able to have. So this is a problem we talked about. Interleaving different users causes problems. System crash causes problems. There can be things where transactions roll back and somebody's read data that was read by a transaction that rolled back. There are all sorts of funny things that go on here. What you would like to do is provide the users the illusion that it's a single-threaded system, only one transaction is running at a time. That would make everything really, really nice. And you know, if you really just ran one at a time, you'd have a failed database system. Nobody would want to buy it. You have a long transaction, it would starve other people. Even if you have a bunch of short transactions, it would starve things. And most transactions do not interfere with each other. So making this all work as if it was a single user system, even though it isn't, that's hard to do. So basically, what is a transaction? And we'll use the word X, X-A-C-T, generally in these notes and in the textbook to refer to a transaction. It's a collection of operations that form a single logical unit, and that we want to be able to have these nice asset properties that we're going to be talking about. So you can say begin, or begin transaction, or begin work to begin it. Or if you don't say anything, as soon as you execute a SQL statement, it'll start a transaction for you. And by the way, you can have a default that each statement is a transaction, or you can have a default that anytime you do a SQL statement, it begins a transaction that has to be explicitly ended. And you can end it with, end transaction, commit work. There are various different things you can say. But the operations that happen in the transaction are a read of something. If you're going to say, well, it's an update, insert, and delete, all of that translates into read writes that occur on the data. That's all that's going on, reads and writes that assume on the data. And of course, it can be on sets of data, not just on individual tuples. But we'll look at this at looking at the tuples that get affected. There are special actions that you have when a transaction implicitly or explicitly begin doing work. And also when you try to commit a transaction, remember, even when you try to commit a transaction or even execute any SQL statement, the database might come back and tell you that that transaction has been rolled back. A transaction is only committed when the database actually makes it all happen, make it so, to quote from Star Trek Next Generation, which is many years ago. When you try to commit the transaction, the database says, okay, it's committed, that's when it's committed. But when you get commit, you might get told, sorry, couldn't do it. You can also, by the way, ask for the transaction to be rolled back inside your transaction. And if you do that, then the transaction will be rolled back. That's one that is going to end up happening. The database won't tell you I couldn't do it. If you ask to roll back the transaction, it will end up getting rolled back one way or another. So the interactions with the database are effectively things that are translated into reads and writes of data. And the begin, the commit, and the rollback. And again, the idea is we'll assume that the database is a consistent transaction a consistent state when your transactions begin. And what we want to make sure is that the integrity constraints that the database knows about are handled by the database, and it remains in a consistent state. Consistency, by the way, means a lot of things. It means physical consistency. For example, you want the B tree to be a correct B tree. You want a hash table to be a correct table. You want the representation of records on your page to be something that's understandable and that physically works. But the database also wants to make sure that logical things that you've asked to be true are true. Such as, again, the values in the domain are of the domain, that a tuple, looks like a sensible tuple, that if you have a constraint to referential integrity, that gets enforced the way that you want it to be enforced. The database knows about those constraints. There can be other application level constraints that your applications are enforcing, but that's up to the application to be able to deal with it. The database only knows about the constraints that you tell it about. It maintains its own physical integrity, and it also makes sure that the logical integrity that it knows about, because you specified that in the schema, that all works. And it enforces that. And will give you an error or roll back the transaction if you try to do something illegal. Now we get back to our friend ACID, and as I mentioned in 180, I always like the notion that databases have ACID properties. And ACID, as you will recall, let's look at what happens with respect to this again, simple transaction where you're transferring $25 from account A to account B. Okay, so the ACID properties are going to be atomicity. Everything happens in the transaction or none of it happens. There ain't no in between. All of it happens and none of it happens. Now, by the way, a transaction could have some branching going on in it, but whatever is the set of operations you've asked to be performed in the transaction, all of them happen or none of them happen. Okay, so if you can't crash after A has been written, your A isn't there. To complete the whole transaction, you have to both write the value of A, write the value of B, and your commit has to be successful. So here you try to subtract from A, write A, you try to add to B, write B. Unless the whole thing happens, none of it happened. So the old copy is still going to be there. Consistency, consistent database, and then a transaction that's working right leaves you with a consistent database if that's the only transaction that you're executing. So for example, you might have a consistency condition that your applications are enforcing. It says that the sum of A and B has to be a constant, or that A has to be less than B, or that A and B have to be equal, or referential integrity. And the database will only enforce the consistent conditions that it knows about, but applications may be enforcing things themselves. Isolation. There are different isolation levels, but we're going to be talking mostly about serializability. I will throw in a whole bunch of CODA stuff about beyond serializability. But the idea is that even though you're executing many transactions at the same time, interleaving them like crazy, the effect is as if you were doing one at a time. That's one of the isolation levels. So the idea is that the executable one transaction is isolated, and serializability is the strongest of the isolation levels that gets discussed. Because it is as if things are going one by one, even though there are a lot of things that are going on concurrently. And then there's durability, which might have been called persistence, except ASIP is harder to say than ACID. You see, if the transaction commits, the changes don't go away even if there are failures. Now, other people can update that data. It doesn't say that nobody else can change the data later, but it says your changes are there. They can be changed by other transactions, but even if there's a crash of a core or memory or whatever it is of the application, the data changes that you've made are still going to be around regardless of the failures of, you know, SSD or disk or non-volatile memory or whatever. It's going to end up lasting. So these are very nice properties to have, and it takes work to be able to achieve them. We're going to talk about this. Consistency is something where the user specifies rules for consistency, and the database tries to enforce them, and there can be things that the application enforces as well. Then there's atomicity, and we're going to talk about the transaction management thing when we talk about recovery and logging, and we'll see how atomicity gets enforced. Then there's isolation. That has to do with, well, we'll talk about two approaches to concurrency control. There are others. The two we'll talk about are pessimistic concurrency control. Pessimistic concurrency control is, let's make sure that we don't have bad things happening with conflicts. So we're just going to prevent it. We're going to lock data to prevent other people from using our locked data in ways that would cause problems. So pessimistic prevents problems. And then we'll be talking about something called optimistic concurrency control. Optimistic concurrency control says, dum-da-dum-da-dum-da-dum, we'll keep track of what it is that we looked at. And we'll keep track of what it is we're writing. And we won't worry about any conflicts. And then we get to the end of the transaction and we'll see, were there any problems? Were my optimistic assumptions good? And if they were, I'll commit the transaction. I being the database in this case. This isn't something that the user deals with. The database takes care of this. So you're going along, everything's wonderful. We're in the best of all possible worlds. And if it turns out the transaction can't commit because something you depended on changed, then you may have to roll back the transaction. But you don't bother taking any locks. You go sailing ahead. If you hit an iceberg, you roll back the transaction. The Titanic goes back to port. It doesn't sink, it just goes back to port. So those are two approaches for dealing with concurrency control, and we're going to be talking about both. And then there's durability, and again, this is the notion of how you end up making sure that even if there are crashes, everything is okay. And we'll talk about write-ahead log, may even talk about write-behind log just briefly, another thing that works with non-volatile memory. But we'll talk about how recovery management is dealt with so that you can end up getting durability even if there are failures. There are lots of techniques for this, but we'll talk about some of the most common ones that are out there. Okay, so that's all going to be showing up. And now, terms. What's a schedule, or as they say in the UK, a schedule? If you prefer schedule, okay, but I'm going to say schedule. What's the schedule? We have all these interleaved transactions that are going on. We are not going to be executing transactions one by one by one. Sorry, that's easy. It doesn't work. Your company fails. Mostly. There actually was relatively recent work in the last 10 years talking about how you might make serial things running one at a time work well, but I'm not going to be talking about that. If somebody's interested, talk to me offline. It's sort of fun to talk about. It was other work that Mike Stoneberger did, and even had a startup company doing that led to a company called VaultDB. That's another story. But we'll talk about schedules in which here we have two transactions that are going on at the same time. And again, with my usual singular lack of imagination, we're going to call them T1 and T2. And T1 is going to read A and write A, and then it's going to read C and write C, and then it decides to roll back. Maybe it doesn't decide to, maybe it tries to commit and it gets rolled back, but there's a rollback that happens. And T2 is going to be running, and it's going to read B and write B, and it's going to commit. Notice these transactions don't do anything involving data that the other one uses, and interleaving these two transactions, whether they commit or roll back, is not going to end up being a problem. So time, the old joke, time flies like an arrow, fruit flies like a banana.
Fruit flies like a banana?
Fruit flies really like banana.
I'm sorry, what?
Anyway, old, ancient, sorry, you didn't hear it before. I've got a million of them. I'm here all week telling jokes. Anyway, okay. I gotta leaven this stuff with something other than just the straight logic of it. So basically, this is a series of steps, and these things are happening, and you see the way the order works. T1 and T2 are interleaved. So a schedule is the interleaving of the actions by a set of transactions where basically all the actions from each of the transactions occur in the schedule. So basically every action in T1 has to be there, every action in T2 has to be there. If those are the only transactions, then only their actions are part of the schedule. It's executing steps one by one, but allowing them to interleave. And they have to also go in the right order. The steps in T1 have to go in the right order, the steps in T2 have to go in the order. So that's the schedule. It's how you interleave the actions of these two, or there could be 27 different transactions going on. So again, we're only talking about the actions that are seen by the database. There could be lots of other stuff going on, but the database doesn't see that stuff. And basically, to say that a schedule is complete is every transaction either commits or rolls back. You will sometimes, including in the textbook, see the term abort, and these days people talk about rollback rather than aborted transactions. So we will only talk about rollback in class. So it's complete. Every transaction that you have either commits or rollback. So it either happens entirely or it doesn't happen at all. And we have this term serial schedule, and serial schedule means you're doing the transactions one at a time. You do T1 and then you do T2. With two transactions, there are only two serial schedules, T1, T2, or T2, T1. You've got 17 transactions, you've got 17 factorial different orders that things could appear in. And if you know the initial state, and you know the schedule, then that determines the final state. Because you're executing time, one by one. The actions are there, they're interleaved, but you're doing each of the actions one by one. And when you roll back, all the actions go, or that transaction go away. And when you commit, all the transactions there, persist, and that's the way it works. And in quotes, which I've added, what constitutes an acceptable schedule? And it's a very nice thing to have. The gold standard of how all of this stuff works is going to be serializability. Basically, if you ran one transaction at a time, that would be serial. And again, your company would go out of business. But instead, you can have the notion of serializable, and we talked about this in 180, and I told you we'd reach behind the curtain and see how all of this actually works in practice in this class, and we're going to be doing that now. So serializable schedule basically says it's as if you ran some complete, meaning again, every transaction either committed or rolled back. You ran some complete serial schedule and got the result. You're not running them serially, but it's as if one of these 17 factorial, if there are 17 transactions, it's as if you ran one of those 17 serial schedules. You're interleaving them like crazy, but the result is equivalent to what you would get if you ran one of those 17 factorial serial schedules. Which one? Anyone? Anyone? It's as if the transactions ran in some order. So could these different equivalent serial schedules produce different states? Well, they're not really equivalent. They're all legal if you're running with serializability, but they could produce different results. I double your salary and then I subtract $10, two different transactions. Different results. If your salary was originally 200 and was originally 100 and I double it, it would be 200, and then I subtract 10, I get 190. If I subtract 10 and I get 90, I double it, I get 180. But serializability means it's some order, and it's okay because it's all equivalent to a serial schedule. All of them are okay. What happens with the roll transactions? They're fantasies. Okay, we will show you how you make them disappear using routing later. By the way, again, when you have transactions that are rolled back, they're fantasies. They might have happened, but they didn't really happen. I used to say using a transaction that might roll back is, building your castle in a cloud, but this day there's so much cloud computing going on that building in the clouds happens all the time. So I'll just talk about it building on a fantasy rather than building on a cloud. Okay? Now, there can be other external actions that matter in a transaction besides rewriting to the database. For example, you might print a value, you might fire a missile, you might open a cash drawer to, make the money available. Basically, for this class, the ways that you deal with this are a subject in themselves. How you ensure that, you give the money to somebody only if the transaction is committed. For purposes of this, we'll basically assume that there are things, it's a long topic about idempotence and how you ensure things happen at least once and at most once, which translates together into exactly once, which again are worth a detailed discussion. I'm not gonna fully go into aspects of that. I'll just give you one idea on this. If a transaction commits, then as part of that, it writes an obligation to open the cash drawer. And it makes sure that as a separate action, not in the transaction, that its obligation gets fulfilled. So it makes sure that it will open the cash drawer once and only once. So once it sees that there's this obligation in the database, it will talk to the physics of the drawer. It will wait until it gets told that that thing has happened. The cash drawer will not open up to give the money more than once. But it'll keep trying until it gets told by the cash drawer, yeah, it really happened. And details of that, go in a distributed systems class. But basically, you want to make sure that you have what's called idempotence. My friend Pat Helland has given talks called, he likes to have great titles for talks. First, let me tell you what the word means, then I'll tell you the title of his talk. Idempotence means if you do something more than once, it's equivalent to doing it once. So if I send a message more than once and the receiving end is making sure that it doesn't take actions more than once, even if it receives the message more than once, then that's idempotent. I'll keep trying until I get told it happened. The receiving end is going to make sure it doesn't happen more than once. It keeps track of messages and it's not going to take the action more than once, even if it gets it 17 times. So Pat Helland has given talks, and I mean this, called Idempotence is not a medical condition. But that's Pat Helland. He's, if you think I tell bad jokes, you should attend Pat Helland's talk sometimes. He's much, much worse. Do you know what immutability is? Immutability means things can't change. Helland has given, it's a great talk, he gives a talk called Immutability Changes Everything. This is Pat. We'll get to some other things about Pat later. Yeah, I'll mention him almost as much as Ray. Anyway, let's go forward. Here's Pat Helland. There is a notion of what he called apology-oriented computing. For example, suppose that you promised to ship something, and it turns out that you can't do it because you promised it to several different people, or because there was a fire in the warehouse, or because the truck had an accident. Then what you do is, you can't undo, but what you can do going forward is you can send an apology and say the delivery is going to take place a week later, or you give somebody a discount on the things that happen. You have to be able to go forward. You try to deal with the external actions by apologizing in some cases, because you can't, the real world gets in the way. You can't always guarantee that the real world action that you promise in the transaction is going to take place. That, as Dr. Strangelove has demonstrated in the movie, which I hope we've all seen, there are some things that are harder to apologize for than others. Mm-hmm. I won't mention Game of Thrones because spoilers. Anyway, okay, so idempotence, as I mentioned, besides not being a medical condition, idempotence together with retrying, if you can keep trying until you're told it worked, and the multiple tries don't cause the thing to happen more than once, that really can end it. Okay, what can happen that causes problems with serializability? Well, this is a variation of an example that I just gave you with the salary. Transaction 1 is going to transfer $100 from A to B, and transaction 2 is going to give 10% interest on both A and B. And here we have what looks like a fine schedule. The transactions begin. You subtract $100 from A, which you're supposed to do, and you write A. And then later on in the transaction, because again we're interleaving these, you're going to add the $100 to B, and you're going to write B, and then you're going to commit. And what's T2 going to do? But we're going to interleave it with A. That's with transaction 1. It's going to multiply A by 1.1. Okay, and write A. It's going to multiply B by 1.1, adding 10% interest, and write B, and it's going to commit. Both of these transactions are going to commit. what each of these does, the green and the blue, are perfectly reasonable descriptions of what those transactions are supposed to do. But the interleaving messes things up. This interleaving messes things up. Why does that happen? Well, at the start, so let's say A is 1,000 and B is 100. What happens at the end of this schedule? What happens at the end of this? Well, okay, you subtracted 100 from A and it became 900, and then you added 10% to A and it became 990, so A is 990. What happened to B? You took B because the blue happened before the green for B. B got changed from 100 to 110 in the blue, and then the green you added 100 to it and it became 210, so at the end it's 990, 210. There are only two serial schedules, T1, T2, and T2, T1. What happens in each of them? If T1 happens before T2, error, then at the end of T1, you're gonna have 900, 200. 100 gets transferred between A and B. And at the end of T2, when you add 10% to them, 900 becomes 990, 200 becomes 220. That's not the same as a result of the schedule you see on the right. But what about, we've got another possibility. What if T2 comes before T1? Well, we're doing T2 first, so we're adding 10% to the original 1,100. 10% added to 1,000 gives us 1,100. 10% added to 100 gives us 110. And now we're going to subtract 100 from each of them. 1,100 becomes 1,000. Oh, sorry, we're going to subtract 100 from A and add 100 to B. So the 1,100 becomes 1,000 because 1,000 is subtracted from 1,100 gives us 1,000. And then we add the 100 to B, the 110 becomes 210. So in the case of T1 before T2, we get 990, 220. In the case of T2 happening before T1, we get 1,210. But what we got with this schedule is 990 and 210. And that ain't the same as either one of those. That's not the same. So this schedule is not a serializable schedule. It's not equivalent to any serial schedule. So basically, what happened is that at this point, A had changed but not committed. B is using a value of A. Now the value of A transaction 1 is going to commit, but basically the second transaction is going to use the value of A that exists in the middle of T1 and the value of B before T1 happened. So that's an issue. The database was inconsistent. There's a write-read conflict because transaction 2 is reading a value of A that might never commit. But at any rate, the value that it reads of A is after T1 messed with A. But the value of B that it reads is before T1 messed with B. So there's a write-read conflict where T2 is reading an uncommitted value of that comes from T1. And that could lead, and in fact in this case does lead, to a non-serializable execution. We showed that. There are only two orders that would be a serial order that would be equivalent to this. Neither one of them works. So this is not serializable. There's no T1, T2, or T2, T1 that works. And those are the only possible serial orders for this transaction. And, you know, hope you had cereal for breakfast. If not, you're having it now. There are other conflicts that can happen. There are write-read conflicts, and there are write-write conflicts that can occur. And those are issues. So what's an example? There are others of a read-write conflict. You have a situation in which T2 reads the value of X, okay? T1 writes X while T2 is still operating, okay? So T1 overwrites what T2 read. And now you have T2 reading X again. So it read X, T1 writes X, and T2, which is still running, reads X again. And it sees a different value of X. It sees a different value that was there. Write-write conflicts, you overwrite uncommitted data, potentially. Let's take an example. Suppose that you have a situation in which students who are in the same group, this never happens in practice, right? Students in the same group are supposed to get the same grade on a project. Seems like a reasonable constraint. And you've got a professor and a TA who are putting grades in on Canvas. And they're putting in the grades at approximately the same time. Canvas has some issues, and maybe not this one, but it does have some issues. And basically, the professor, who's very generous, wants to give both students an A. And the TA, who's much tougher, actually, you've got good TAs and graders for this class, readers. The TA wants to give both students a B. Both of these are entirely reasonable. If they were executed serially, both students would have an A or both students would have a B. But let's see what happens, right? The professor writes an A for X. The TA writes the B for X. The TA, who's really fast, the professor's slow, I'm a slow grader, that's true. The TA writes the grade for B, for that Y gets a B. And now the professor writes an A for Y. What's the result? Both of them did what the transactions were supposed to do. The professor wrote an A and an A for both students. The TA wrote a B for both students. But the result is going to be that Y gets a B, that you end up having an A for Y and a B for X. So the students don't have the same grade. And there aren't even any reads here. We just wrote the results. So this is not a read-write conflict, it's just a write-write conflict. But usually you get write-write conflicts often typically together with read-write or write-read conflicts, because this notion of doing blind writes where you don't read what's there before putting something in, it's unusual. It does happen. Again, if I'm setting a grade, I may just set the grade without looking what's there, but generally you read before writing. So write-write conflicts usually do come together with read-write and write-read conflicts. Okay? Well, let's go back to this building based on a fantasy with the rollback transactions. The definition of a serializable schedule is, it's a schedule. In fact, it's a complete schedule which is equivalent to a serial execution of the committed transactions. The rollback transactions never happened. So to have a serializable schedule, it has to be a serial schedule, which again means complete, every transaction committed or rolled back. But it's equivalent to what would happen if just the committed transactions happened in some serial order. Okay? What committed happened. But several issues. Number one, the rollback transactions did stuff. How do I undo that? I want to be able to do things in the database in case they did commit, but maybe they didn't. And if they didn't, I want them to go away. And moreover, and we will go over that in detail when we get to locking and recovery later in this sequence of lectures on transactions. But what if the second transaction saw the effects of this rollback transaction before they were undone? You want to be able to make a lot of progress in your transactions. I'm reading something. I'm hoping it's going to commit. Maybe it does, and maybe it doesn't. And if I read it, I'm undone too, or at least I have to be. If I read the effect of a transaction that was undone, I made a decision.